All right, got a few questions, several panicked questions in the chat. So, seems to revolve around when do we use easy cis trans and why do the solution packets tend to bounce back and forth? How do you know when to use it? So, um, honestly, really a lot simpler than you think. So, let's go back to why we have to use easy versus cis trans, or why we're having to use any of them. So, when it comes to, I'll use a C even though C is an element. When it comes to alkenes and cycloalkanes, we don't have carbon-carbon bond rotation. So with the rings, you can't rotate around a single bond because they're in a ring, they're kind of locked. With alkenes, we get the same effect, that this double bond prevents carbon-carbon bond rotation. So now this creates spatial orientation. It limits the degrees of freedom. And so the reason why we need cis-trans EZ is to describe relative orientations. If we flip A and B here, there's no way to get it back. So if we had something like this, we can rotate around this bond to get A and B to flip, but we can't do that anymore with a double bond. So the question is, when do we need cis-trans versus EZ? Well, in the big scheme of naming alkenes, every alkene that requires this notation can be named by EZ. But there's a special case within this where cis-trans works. So EZ is the most universal way of naming alkenes that are not terminal alkenes. So terminal alkene, you don't have to use the cis-trans EZ because there's no meaning to it. But if you have a non-terminal alkene, you have to use EZ, or there are special cases where you can use cis-trans. So we prefer the cis-trans if we can get away with it because it's easier and faster. EZ is more rigorous, and that's why we try not to use it if we don't have to. So when do we have to use it? Well, cis-trans is a special case where we have the same groups on both sides of the bond. So either A and C are the same, A and D are the same, B and C are the same, or B and D are the same. This is the special case for cis-trans. So EZ works by the Kohn-Ingold-Prelog rules, the CIP. Those are the same ones you use to assign cis and or use to assign R or S. And so with the CIP rules, you look on both sides of the bond, and we assign a priority to these based on atomic weight, branching, same things we did for R and S. And then for the C and D side, we do the same thing. And if the highest priority group is on the same sides, let's say highest groups, they're on the same side. So when I say the same side, I mean if we cut through the bond, if they're on the same side, both top, both bottom, this is, sorry, camera up a little bit there. If they're on the same side, this is Z, zusammen, or together. If they're on opposite sides, they're E, they're entgegen, they're opposite. And so the Z just means the highest priority groups are on the same side of that, same side above or below the bond, whereas the E says they're on opposite sides. So in this case, this would be B and C are both highest priority, or A and D are both highest priority. So why do we have this special case? Well, for the CIP, we have to assign priorities of both sides. This takes time. If we have two groups that are the same size, they have the same priority. Now, they aren't necessarily the highest priority or lowest priority on their respective sides, but they are the same priority. So two bromine atoms have the same priority. Two CH3 groups have the same priority. Two hydrogen atoms have the same priority. So with the cis-trans, what we're saying is that this is a special case where if they're cis, they're on the same side. And if they're trans, they're on the opposite sides. So it's a special case. And we like the cis-trans because it's a lot easier. We know two chlorines, like we have two chlorines, they're the same priority. If they're trans, they're just going to be on opposite sides of the double bonds. If they're cis, they're going to be on the same side of the double bond. There's no need to work for the Conical Prelog rules for the two other groups that are on this double bond. So if you see two atoms, two groups that are the same on opposite sides of the double bonds. So let's say instead of having A, B, C, D, we have A, B, B, and D. Now you can jump to cis-trans because you have two groups that have the exact same priority. But if they are four distinct groups, so methyl, ethyl, chlorine, fluorine. In this case, you have to use the EZ rules because there aren't two that have the same priority. And that's the tip-off for cis-trans. Cis-trans works because there are two groups that have the same priority. And so if you have four groups with all different priority numbers based under the Conical-Prelog rules, then you have a situation where you can't use cis-trans EZ. Now, EZ will always work. So if something can be named by cis-trans, it can be named by EZ, but not the other way. So if something can be named by EZ, it may not necessarily be nameable by cis-trans because we may not have two groups that are the same. So the key will probably consistently work with EZ because that always works. But there will definitely be times where you see cis-trans. And the thing is that if you have cis-trans, you can use EZ. If you use either cis-trans or EZ and they're both applicable, your answer is still right. The cis-trans is just easier, particularly when we go backwards. So when it comes to taking the name and going to the formula, the EZ gets daunting because we have to draw out the molecule and hope that we get the EZ right and then check it. Whereas with the cis-trans, it's really obvious. We just draw the two groups that are the same on the correct side of the bond and we're done. Now, where was I going with that? So cis-trans, the two groups are the same, easier to draw. Oh, cis-trans and EZ are not one-to-one correspondence. So cis isn't E isn't Z and trans isn't E. In 90% of cases, it will be. And that's kind of what gets people in trouble. In fact, when I was tutoring organic chemistry before I started teaching it, I got me in trouble was like, I don't understand why cis isn't always Z and why trans isn't always E. There are some 10% of cases, they aren't really esoteric cases, but they're also not very common cases, where you start introducing like halogens or ethers or things to this that are like heteroatoms, they're not carbon and hydrogen. So if you just have an alkene, so no alkyl halide, no halides, no alcohols, pretty much always cis-trans and EZ will have that one-to-one correspondence. But once we start putting alkyl groups or alcohols or anything else on these things, particularly around those double bonds, E and Z may not agree with cis-trans anymore. So again, there can be an esoteric case here. Let's say we have CH3, fluorine, chlorine, and bromine. Oh, actually, no, I need the two groups to be the same for this to work for I think this will work. Let's work it out. So with this one, this is a trans. Actually, I can't do this one because it's a terminal alkene. So let's have an alpha group. So in this case, this would be trans 2 chloro 3 methyl pentene. So we have 1, 2, 3, 4, 5, and this ends up being trans because of these. So the trans here, we have to have two groups of the same priority. Your methyl groups are the same priority, so that's what makes them trans. And thing to keep in mind, the cis-trans usually is referring to the hydrogens. This is a special case. I shouldn't say the special case. Usually what you'll see in example problems is usually the cis-trans is referring to the hydrogens because they have the same priority. In this case, we have two methyl groups that are the same priority. Now, how does this work by EZ? Well, it's still the same name, 2 chloro 3 methyl pentene. But if we look at the priorities here, so chlorine here is top priority, methyl second lowest priority. Here we've got, again, this is the 1 priority, this is the 2 priority. Oh, this is a bad example because they're also still opposite. Actually, we can do this with all right, let's work another example. Yeah, these are hard to come up with off the cuff. The exceptions are very hard to come up with on the, and I shouldn't be calling them exceptions. It's just the rare examples are hard to come up with off the cuff. So let's do can we do cis-trans with this? I don't think we can do cis-trans with this. All right, this will work. So this is your 2-chloro-2-butene. And this is going to be cis. So the cis here, we have two CH3 groups, so they are the ones that are cis relative to each other. Now, still got the 2-chloro, 2-butene. Now, the equivalent in cis, same side here, is going to be Z. E is going to be opposite. But if we start looking at the priorities, on the left side here, this is the #1 priority. This is the second priority. This is the number one priority. This is the secondary. So now these are opposites, and these are E. So in this case, the two high priority groups aren't cis, they're opposite, so they would end up being E. And this is why they end up looking different sometimes. This is why E and Z and cis-trans don't always agree with each other, is that they rank priority differently. So cis-trans is comparing two groups that have the same priority, whereas EZ is comparing the highest priorities. The ones that have the same priority may not be the highest priority or lowest priority on both sides of that bond, and so that's why occasionally cis-trans and EZ will disagree. Now, the reason why I pretty much always work cis-trans and EZ agree for alkanes is that your priorities are just the branches. Well, if they have the same priority, they're probably going to be the same priority on both sides, like regardless of whatever else is bound to them, because they're all going to be hydrocarbons. But if I were doing problems, I would do everything in my power to name by cis-trans. Just not because it's harder to name EZ, it's harder to go backwards from EZ. Yes, so cis-trans only works if you look at the double bond, and on both sides of that double bond, you see a group that's the same as a group on the other side. So if you have two methyls, two ethyls, two hydrogens, two chloros, two fluoros, two bromos, anything that's two the same, it'll work. But if you have 4 different groups bound to that double bond, that's when you're stuck using EZ. Those tend to be rare cases, but we do need the problem with cis-trans is that, again, it requires the two groups to be the same priority. If you got 4 groups, they don't have the same priority, so that cis-trans doesn't really make sense because there's no 2 groups with the same priority to say, oh, these are on the same side, they're on the opposite side. Then we drop into EZ, it's a lot more rigorous, but it takes a lot more works. Correct. So if all groups are different, you have to use EZ. So if you look at the double bond group, the group A, B, C, D, and all 4 different groups, you're stuck using EZ. They're harder problems, but they do come up. If there are 2 different groups that are the same, you can use both cis-trans or EZ. It is your preference. The key pretty much just used one or the other. But if it's 2 groups are the same, you can use cis-trans and you're still going to have the right answer. Yes, so hydrogens are the 2 groups with the same priority. They're the lowest priority by CIP. So that's typically when you see cis-trans for like complicated alkenes and you want to know why. How are they saying this is cis-trans, this complicated molecule? Because you look at the double bond, it's probably 2 hydrogens. And yes, and it can be any 2 groups as long as they're the same group for cis-trans. So methyl, ethyl, butyl, tert-butyl. You can do, if you look at decane, 1, 2, 3, 4, 5, 6, 10. So you've got 5 decene here. This is the cis, this is the trans, and the cis trans here refers to the hydrogens. And we can make this asymmetric. But we can still use cis trans because we both still have two hydrogens and they're the same priority. And that's all the cis trans is saying, is that the two groups of the same priority are on the same side or opposite sides. So yeah, that's why I say it's really not as bad as you should worry about. Like it's more cis trans is a shorthand, and we use it when we can because easy is a lot more work. Easy will always be right. Like if you put easy, you will always be correct. With cis trans, you may not be correct if you kind of misjudge it and said, oh, these two are the same. So the way I get students to check is ask yourself cis to what and trans to what. So if you're saying, oh, it's a cis molecule, cis to what? What two groups are cis to one another? If you can't tell me what two groups are on the same side, because you'll say, well, the two halogens is like, how do you know it's referring to two different halogens? How do you know it's not the halogen in an ethyl group or the halogen in a methyl group? Yes, for easy, it works on CIP rules. That's part of the reason why when we do the RS the way we do at the start of the course is to get you familiar with the CIP rules. So with alkanes and alkenes, you're kind of familiar with the rules now. You kind of know how to work with it. And the nice thing is, like, we are to the point now that there's heteroatoms. There's things other than carbon and hydrogen, so the CIP rules are getting a lot easier to work with. And we try not to like work with super esoteric hard examples. Like you can definitely invent examples that are super daunting to work through. But if you can do simple examples, you can do the daunting ones. This isn't an exercise in how much algebra you can carry out. It's an exercise in do you understand the concept. And if you can name the simple compound, you can probably name the more complicated compound as well. All right, glad to hear that. Other questions out there? Yes, Markovnikov's rule. So when we did elimination, and I'm going to talk about elimination because actually Markovnikov's comes from Zaitsev's rule. So when we did elimination from a halogen, from something like this, and we're not worried with the stereochemistry because we're doing elimination, and we did elimination, we always eliminate it from the most substituted carbon. And so if we eliminate this, we go by elimination, we'll pick off this hydrogen here instead of this hydrogen here, and we'll end up getting this alkene. Now, this has to do with the stability of the carbocation intermediate. Actually, this is a bad example. So, back up, because that would give you carbocation rearrangement. So let's say we're going to do elimination. Again, we're not going to work with the stereochemistry on the starting alkene. It's not important to our discussion. So if we do elimination, we can eliminate hydrogens from 2 spots. And the question is, which spot do we eliminate from? And we're going to eliminate from the most substituted one, and this is your Zaitsev's rule. So Markov-Nikov is just the reverse of this, to say that, well, we probably eliminate, because we don't know the history of this molecule. We don't know how it got here. So if we're going to add back, we're going to add the hydrogen to the more, we're going to add the nucleophile to the more substituted group. The idea here being that if we form a carbocation, we want to form it on the most substituted carbon. So Markov-Nikov here assumes a carbocation. So it's going to assume that we're going to add our nucleophile back to the most substituted carbon, and we're going to add a hydrogen back to the least substituted carbon, because that's how we would do it through an E2 elimination. The nucleophile would be lost, or the leaving group would be lost off the most substituted carbon, and then we'd add a hydrogen back to, we'd take a hydrogen off whatever group had the most substitutions. So where this comes from, where Markov-Nikov's rule comes from, is the mechanism itself. So let's say I have this starting molecule, and I know I'm going to add back to the double bond, and I've got 2 components here. I've got my nucleophile, and I've got a hydrogen. And this is my electrophile. So there are 2 ways I can make this happen. But in both cases, I'm going to go through a carbocation intermediate. So I can either knock this double bond up, generate this structure, I can knock it down, generate this structure. So I have a carbocation and I have a carbanion, a negative carbon. Now, this is not really what happens, but it's a good way of illustrating it. So the question is, what's more stable? A tertiary carbocation or a secondary carbocation? And you should know by now it's the tertiary. So since the tertiary carbocation is more likely to form, this is where this negative nucleophile is most likely to attach. It more easily creates a positive center for that nucleophile to attack, and then your negative here attacks the hydrogen. So generally speaking, when we add to a double bond, Markov-Nikov's rule says that we're going to add the nucleophile, whatever isn't hydrogen, but it's being added to the double bond, that's going to go to the most substituted carbon, and then your hydrogen is going to go to the least substituted carbon. Now, your double bonds have a top and a bottom. They are trigonal, both these carbons are trigonal planar. So depending on how this addition works, where's my modeling kit? So this is 1-methylcyclohexene. Your double bonded carbons here are flat. There's a top and a bottom. So if I take my cyclohexene ring and I put it on its side, there's a top and there's a bottom. So this syn versus anti-addition is going to depend on what reaction we're carrying out. Hydroboration, that's what's referred to as a syn addition. Halogenation is an anti-addition where they add on opposite sides. So the anti or syn here refers to how the nucleophile and how the hydrogen are added back to the double bond. An anti-addition results in a trans product. So what happens in an anti-addition is one's going to attack from the top and the other is going to get attacked from the bottom. And so what happens is they get added to opposite sides of the face of, well, rings are the easiest ones to see. But what will happen is that if we look at the double bond, we're going to have one thing coming from the bottom and another thing get added through the top. So that's an anti-addition. A syn addition looks cis. So whatever we're adding is going to get added to the same side, and that's how I always thought it was: syn is same side. Now, most reactions follow anti-addition by their mechanisms, but there are definitely exceptions. This is why I'm not the type of instructor that really emphasizes mechanisms, because I think the mechanisms, you kind of like, it's too much information to comprehend. The big thing is to memorize the end product. So again, hydroboration, there is a mechanism for it, but with hydroboration, it's an anti-Markovnikov, meaning that that alcohol that you're adding goes onto the least substituted carbon, and it's a syn addition, so the hydrogen and the OH are added to the same side. Halogenation, hydrogens are added to the same side. Mechanism kind of helps explaining this, but generally speaking, you don't need to know it. But halohydrogen addition, where you add the OH and a halogen, the OH goes to the more substituted carbon, the halogen goes to the least substituted carbon, and they're going to end up on opposite sides. The OH and the halogen are going to be trans to each other on that ring. But yeah, syn, anti, syn, same side, anti is going to be opposite sides of the double bond, and you can get them flipped. That's what makes anti harder, is that one can attack from top, the other from the bottom, or flipped, one can attack from the bottom and one up from the top. So you're going to get both mixtures when you do an anti-addition. With a syn addition, you typically only get one set of enantiomer, one set of stereoisomers. I think I had 5 A's on that exam. Yeah, you're welcome. As far as what they did to study, I can't tell you what students did. I can't tell you other students' grades, like that's protected by FERPA. So you'll just have to ask around the class. But no, I can't tell you who got an A and how they studied. You'll have to ask them. But by law, I can't disclose to you any other students' grades. I can give you vagaries saying like, oh, 5 people got A's, but I can't tell you who those 5 A's were. Sometimes it helps just to have somebody talk through it with you. So this is why we have the live streams, is like if you need someone to talk through it with you. Now, in terms of the material itself, if we use a foreign language analogy, I think alkanes are the first time you actually start doing conversational organic chemistry. The first test, the NMR, the characterization, the drawing, that's all kind of like when you learn the alphabet in a foreign language. The second test with naming alkenes, that's when you start learning like nouns, verbs, the different words. Test 3, where you did the alcohols, alkyl halides, I think that's kind of the first time you really start constructing sentences, but they're like simple sentences like, where's the library? This is my name. What is your birthday? And then I think alkenes is the first time you really start carrying on conversations, particularly synthetically, because there's a lot more you can do. You're to the point that you can make alkenes. Once you can make an alkene and react it back into something else, you have a lot of flexibility. And this will definitely show up if you go into organic too, is that, yeah, there's a lot that kind of like you can do synthetically once you produce an alkene or once you produce an alcohol. Once you've got that, there it gets a lot easier. Now, you don't retract messages. Yes, at this point it's memorization. So you need to memorize what the reactions. Um, Best ways to memorize the reactions. What do they react with? What do they produce? And what are the products, like in terms of stereochemistry? Is there anything relevant for the stereochemistry? Now, hopefully you'll pick up about half of these reactions are just alcohol reactions run in reverse. So if we take something like this and we add HCl, you'll get this. Well, the reverse of this is just like tert butoxide. So we're adding an acid to get this addition, or we add a strong base to get rid of everything. So HCl, you're going to end up with mixture. You're going to end up with mixtures. So make sure you know the stereochemistry of the mixtures. Name the reactions. I don't have. Give me a minute to go grab my flash drive. I'll be right back. So in terms of the reactions, you're going to need to know by the time this is done. You need to know the halogenation of alkanes, which was test 2, so that halogen plus free radical or peroxide gives you substitution at the most substitute carbon. From the alkyl halides, elimination E1, E2, nucleophilic substitution SN1, SN2, conversion to alcohol. Oh wow, I need to update this. Oh yeah, I kind of need to update this list. For alcohols, elimination, nucleophilic substitution, alcohol conversions to alkyl halides, phosphorus tribromide, thionyl chloride, tosyl chloride, and POCl3. And then for alkenes, hydrogenation, H2 platinum, HX addition, so HCl, HBr, HI. And then those reactions, but if you add light or peroxide, you get the anti-Markovnikov. Hydroboration oxidation, that's B2H6, H2O2, and 2. Hydration, water and acid. Halogenation, halohydrogen, epoxidation, Diels-Alder, and alkene metathesis. Ozonolysis, Simmons-Smith. And bromosuccinide, free radical halogenation, and potassium permanganate. So what I can do after this actually wouldn't be a bad idea to post. Let me get a pen really quick. So what I give the Organic 2 students when they start out is a summary of all the 251 reactions we teach. And it just says reaction, reagents, what the reactions are, what the products are, what's the stereochemistry, and any comments. And that's basically flashcards. The hardest one we're going to learn for this test is Diels-Alder, but there is a trick for learning Diels-Alder. The other thing with, so I don't know when this cut off. Man, there's some lag in this today. So what I'll do after this, and I'll post it, it's a table I give the Chem 252 students. It's just a table summarizing all the reactions from Organic 1. It's a table you should be able to fill in. A few things to keep in mind about the reactions with alkenes, and I try to talk about this a lot in the PowerPoints, is they're actually all kind of the same reaction. You're just changing what gets added to which end of the double bond. So you've got your first thing I would do is say memorize all the Markovnikov reactions. So basically what's called HX addition. So with HX addition, if you have a double bond, when we add these two together, X goes to most substituted carbon, and then the hydrogen goes to the least substituted, and this is going to be, I think it's an anti-addition. So you're going to have both forms. Now, once you've learned the HX additions, and keep in mind, X can be a lot of things. So X can be iodide, bromide, chloride. You can have H2O, and so when you see the H2O plus acid reaction, that's all that is. Make sure I got the summary here in front of me. So these are all the Markovnikov. The anti-Markovnikov, or AM, as you'll see it abbreviated occasionally, basically we add X to the opposite side. And the way we flip these Markovnikov reactions to anti-Markovnikov, these are flipped with lighter peroxides. This is flipped with hydroboration oxidation. So memorize the Markovnikov and then learn how to make it go anti-Markovnikov. Now, there is a special case of Markovnikov, or I'm going to call it a special case, where instead of using hydrogen, we have a halogen. And so this is your halohydrogen addition. Instead of having hydrogen, you've got a halogen, but you're still going to add this OH group to the most substituted side. Halogenation, you just add them both. You just add both alkenes. And then the rest are kind of memorization. So N-bromosuccinide and free radical halogenation, so NB should be NBS in this sheet. They have the same effect. Let's say you want to add a halogen to this, but you don't want to add it to this double bond. In this case, you use either the halogens with light or you use NBS. But yeah, there's a lot of reaction to memorize, but a lot of these fall underneath the same umbrella. All the Markovnikov and anti-Markovnikov, they're pretty much the same reagents. You're just changing reaction conditions. And then there's a few additional ones to memorize. But the hardest ones to learn are Diels-Alder and alkene metathesis. The alkene metathesis, we're going to stick to simple cases of it. It is a reaction that can quickly get very, very complicated if you're not careful with what alkenes you're working with. And then the big thing about Diels-Alder is the stereochemistry. But this is why when I teach it, I teach you to name the diene and the dienophile differently, and then compare them to the final product. So with a Diels-Alder, you always produce a one cyclohexene ring. If you know how the diene and the dienophile fit into that, it's just a matter of numbering the carbons in each one and then attaching those appropriate groups to it. So Diels-Alder synthesis. Because I'm kind of trying to speak about generally, and it's just something better if you see a specific example. And again, you're probably not going to be there yet in terms of knowing how to do Diels-Alder, but it does show up later in the notes. So with Diels-Alder, we have a diene and a dienophile. And they're going to come together to make, but there's always this group. So there's always these four atoms, double bond, single double bond, and there's always this double bond. These 6 atoms will come together to make cyclohexene. So the way I advocate you learn Diels-Alder, identify these 4 and number them. 1, 2, 3, 4. And take these 2 and label them with letters. I do alpha and beta. So This double bond always appears between the second and third carbon. And there's your first and second, and your alpha and beta. Now, you can always flip these, and you'll see this in the notes. These can quickly become complicated problems. But what you do now is you just write out what's bonded to these. So 1 doesn't have anything bonded to it. 2 has a methyl group. 3 has a methyl group. Alpha has 2 methyl groups, and beta has 1 methyl group. And so that's how you can predict how things are arranged in that final product, by doing this numbering and this lettering. But again, you'll see in the notes, these quickly get complicated if you don't have symmetric diene and dienophiles. So probably for the test, you're looking at like much simpler like dienes and dienophiles. So you probably have something that looks very symmetric. Like that. And there's a whole theory backing up why Diels-Alder occurs. I'm just not a huge fan of teaching that theory. I think it's interesting. Like, if you really want to understand the mechanism, I think it's interesting. But it's another one of those, I think you can lose the forest in the trees problems. Like, I can give you all the information on how the mechanism works. It's very interesting. But it doesn't really kind of help you predict the products. Drawing that cyclohexane ring really helps you draw the products. Now, the other thing I find fascinating about Diels-Alder is what's called retro Diels-Alder synthesis. And the reason we're having to focus on this actually used to be a question for a makeup lab, because when spring 2020 hit, I was teaching organic and we didn't have any alternative labs. Like middle semester, we had to go completely online. And it was, for me, fascinating because I could actually talk about a particular type of Diels-Alder problem. So for Diels-Alder, you need a diene and you need an alkene. But the thing is that this is a diene, but it's also an alkene. And so 2 of these things can come together. And this double bond will react with these. And so you end up getting this structure here, which is called dicyclopentadiene. And they don't even, that is not IUPAC naming whatsoever. This is cyclopentadiene. Dicyclopentadiene is called that because it's literally just 2 of them fused together. If you look at the actual naming rules for circles and alkenes, this isn't true. But the reason they call it that is for very practical reasons. If you heat this, it'll actually take this and decompose it. So when you buy cyclopentadiene, it doesn't look anything like this. It looks like this. And I've actually had to run this reaction where you heat it up to decompose it back into cyclopentadiene. But it's come up because we want to do a Diels-Alder lab, and we've ordered the chemicals for it. We know what we want to do, but the big thing was we were looking for cyclopentadiene. It's like, well, you can't buy that. You have to buy the dicyclopentadiene and then decompose it back. And I don't really see how Lewis theory predicts that if you just heat this, it'll go back to this. You never see Diels-Alder written with reversibility arrows. But in some cases, Diels-Alder is actually reversible if you heat it up. And I had no idea, looking at a molecule, how you would know that. Like looking at like, oh, I could decompose this back into the Diels-Alder precursors. I have no idea how you would figure that out practically, except through just like going through thousands and thousands of examples and having that context. So yeah, we're going to stick to simple examples of Diels-Alder with this, and we're not going to worry about like retro Diels-Alder. I think it's fascinating. It's super hard. Professor should say it's outside the scope of this course. So yeah, after this live stream, what I'll do is I will post these summary tables to the test for material. There will be a blank, and then there will be a there'll be a blank version, and then there'll be one that's filled in depending on what your learning style works best with. But hopefully that will help you in terms of understanding the materials, that it'll kind of give you a summary of what reactions you should know so far, and then a summary of the reactions you need to know for this test. And this also has alkynes in it because it is meant as a 252 review packet. For the alkynes, you're not going to know these yet. Hopefully what you'll notice with the alkynes, though, is that if you compare them to the alkenes, alkynes are really just alkenes with an extra bond. And then we do reactions of ethers, and there's only 3 of those. 2 for making the ether and 1 for breaking it apart. So yeah, it's a very short worksheet. The purpose of the lab this week with the distillation lab was to give you much more experience with assembling the glassware. So we have to give you pretense though. So we just can't like say, oh, go to the lab and practice assembling glassware, because you're not going to learn anything in that. But to say you need to assemble the glassware in order to run a distillation, both a simple and a fractional, now you've got context, and there's an end result here of you producing the data and calculations. But it's a very short, in terms of data analysis and calculations, it's going to be very short, because the purpose of this lab is not so much for you to learn how to do the calculations. You already know how to do density from Chem 1, Chem 2. The big thing was getting you that hands-on experience with the distillation column, because that's what you'll be working with for the dehydration of cyclohexene lab. You're going to basically make the mixture and then distill it to get the pure product. You're welcome. Second problem on... I'm assuming it's not naming. God, you're going to have so many stereoisomers with some of these. Alkenes, page 10. All right, mercifully an easy one. So we've got HCl adding to this. This is going to be a Markovnikov reaction. So our most substituted carbon is this one here. So this is our X. This is our H. Now the question is whether or not we need stereochemistry. And if we look at it, on this carbon, there's a chlorine, bromine, but then there's two ethyl groups, so there's no stereochemistry. So this would be your final product, would be the 3-chloro, 3-bromo, pentene. Now, the one beneath it, this just makes it anti-Markovnikov. And with the anti-Markovnikov, instead of adding the chlorine to the bromine, we're going to add it down here. But the thing is, now we've created two chiral centers. And the problem with alkenes is you always get a racemic mixture if you're going to create chiral centers. So we're going to have all 4 enantiomers here. So we're going to, you'll see it in the key, drawn out more. We'll do a squiggle line. You'll have both the R and the S, so there's 4 combinations here. RS, RS. You're welcome. Organic chemistry is very much a mindset and a way of looking at the world. So part of the reason why you're given so many examples is not to memorize the examples, but simply so you can start, hopefully begin to see by going through the process what the thought process is. And because the exams are all just variations of the same, like version A and B are the exact same problems of the exams, it's just that one has a different molecule than the other, but the concepts are the same. And I know that's easy to say as someone who's like taught it and worked on it for a while. But again, that's kind of the hope, is that you'll get a feel for the mindset. right, that kind of seems to be it for the questions for today. So again, live streams are here in case you got questions. These aren't lessons, these aren't lectures, they're office hours. But I do enjoy the conversations when they show up. So thanks for coming. And I will see you all Monday.